This video demonstrates some of the capabilities of the EasyFlowfield code. This Windows 10 application simulates inviscid, laminar, and turbulent flow using a range of explicit and implicit solvers. It offers substantial capability without costing thousands of dollars. It comes with tutorials, validation test case files, and help files arranged under each of the columns in the GUI. This GUI is used to create scripts that are then run to simulate flow under various conditions. This shows the grid used to simulate Mach 0.0005 laminar flow about a NACA 12 airfoil. It's solved using an implicit scheme with preconditioning. Now, EasyFlowfield comes with a number of demonstration simulations, and these scripts are stored in a common folder, and they all share the grid folder, common grid folder, and an output folder, and they can be run one at a time. It's more convenient to run the simulations in project folders so that you can keep the output from each particular simulation. I'll be starting and running a number of simulations before I actually start demonstrating how to create a script, and these simulations will be running simultaneously. The first simulation involves turbulent flow around a backward facing step. This is a 4-block grid. The blocks are created internally by EasyFlowfield, and you only have to specify a number of cells in each direction, and the boundary conditions on each face of a block. And in this particular case, you're controlling the distribution of cells along the block faces using edge controllers. Otherwise, you control them by these parameters here. Now, EasyFlowfield can create multi-block grids in 2D, but 3D multi-block grids can be imported. Now, these blockage controllers are simply used to specify the cell thickness at each end of a grid face, and they can also be used to connect adjacent grid block faces, and instead they can just be used for node placement only, or for spatially periodic boundaries between two sides of a grid. And you can also impose a curvature on some side of the grid simply by selecting a curve which contains points input from a file, and there you can see how it's deformed the edges of two adjacent blocks. Now, I don't want to do this in this case, so I'm going to turn that off. Okay, now I'll just save this script. EasyFlowfield assumes that if I've opened and closed a dialog, then I might have made some changes, and then I will run it and go on to the next simulation. And this involves turbulent flow about an airfoil. And this is the RAE 2822 airfoil. And the output from this simulation will be compared to experimental points, and they are obtained, the conditions for the simulation are obtained from the NPark Alliance Validation Archive. And when I'm finished this video, you might be interested in comparing my results to the results of NPark codes. Now, in order to run a turbulent simulation, you must specify a viscosity model, which in this case is I'm using the Sutherland equation to compute molecular viscosity as a function of temperature. You can also specify coefficients to compute specific heat as a function of temperature. There's other cases where you can specify the thermoconduction instead. And you have to specify a turbulence model, which in this case is the K omega 2006 model of Wilcox. In this fine grid, I don't need to use a wall function, but I could have used a coarser grid with an automatic or adaptive wall function, which will handle very small cell thicknesses near the wall. And you could use a standard wall function, but that will not handle the small cell thicknesses. Once you've chosen the viscosity and turbulence model, then you have to choose. So you could have run an inviscid simulation, a laminar simulation, but in this case I'm running a turbulent simulation, and I'll only discuss this parameter here, which is being set to the size of the chord, which is 1 foot, but expressed in meters, and that is used as a reference length to output the Reynolds number based on chord, which will be discussed later in this video. Now, in order to run this, you need to specify a state, which in this case will be a Mach state. You specify the pressure and the temperature and the Mach number at the far field, and the angle of attack is expressed as a negative flow angle. And in this case, if you wanted to, you could also specify conditions on the wall. These might include wall roughness height and suction or blowing on the wall, and you can also specify these conditions on a portion of the wall. You can also specify a thermal flow condition, which in most cases involves specification of the wall temperature. And if you use an adaptive wall function, you can also use this roughness height. Now, this simulation uses an O-grid, and it uses the airfoil points, which are read from a file in various formats obtained from the various sites on the internet. In this case, I've specified number of cells as 256 around the airfoil and 96 cells for the far field. I'm using a chord again as 1 foot, and I'm using a 25 chord far field distance. In order to use a fairly small distance, I'm using a vortex correction at the far field. Otherwise, I'd have to use maybe a 100 chord far field distance. And I'm using a wall data boundary condition on the wall of the airfoil, but I could have used a no slip in this case because I didn't use any special conditions. And I specified an approximate boundary layer size. This is around mid chord, and I'm going to increase the size temporarily to show you something on the comparison of the grid to the input points. So I'll close that. And I'll zoom in to the trailing edge, and you can see there's quite a good correspondence between the input points and the final position of the airfoil walls. Now, some of the files you can get from the internet do not have a closed trailing edge, and EasyFlowfield closes the edge for you, and the trailing edge for you, and gives you a warning this has happened. And I'm going to zoom out, and I'm going to increase the concentration again back to the original value, which is -5, and then I'm going to zoom into the grid at midchord to examine the cell thickness next to the wall in that area. And then simply by drawing a line from down to the wall, you obtain the thickness of the cell, and it's a little bit less than 1/1,000,000th of a meter. And please remember this figure, because I'll be referring to it later in the video. Now this simulation is being run first on a subgrid, and this subgrid has 1/2 the number of cells on the around the airfoil, and it's run for 3,500 cycles at a CFL of 400. And this is run using an implicit scheme, which is a slightly higher CFL number after the simulation has been run on the subgrid. And it's being run without multigrid, but it could in fact have been run with multigrid depending on the type of simulation I'm doing. And I'm using a super B limiter, which is fine as long as I'm using an implicit solver, but normally would not be used with an explicit solver. Now, I can output various types of output. The one of most interest in this case is the output of the conditions at the surface of the airfoil, and in this case I could have specified pressure coefficient and friction. What I would ordinarily do, but because experimental values of friction were computed in a slightly different way, I've output the primitive variables plus friction velocity, and I'll show you later how that is being used. And I'm normalizing by the chord because that's the way the experimental values were also provided. Now, this was run using an internally generated grid, but it also can be run using imported grids, either in the CGNS file format or in the plot 3D format. CGNS format can store the boundary conditions and the block connections, but plot 3D file cannot, and in that case you would have to impose these boundary conditions using a number of dialogues, and you also can impose the block connections, and you can also impose a gravity field if desired for certain simulations, and you can also vary the equation angle of attack to obtain a desired value of lift. You can also specify steps in angle of attack over a specified range that can be used to produce plots of lift and drag versus angle of attack, or drag versus lift. Now, you can also export files in CGNS format or in plot 3D format, and in this case you can also reduce a suitable 3D grid to a 2D grid. You can also export suitable 2D grids to a 3D grid type. You can add quite a few cells in the Z direction and control the distribution of cells as well. And you can also output the airfoil forces, in this case lift, drag, and pitching moment, and in this case you're using the coefficient of pressures, integrating them around the airfoil, but also using the friction to compute the drag. So I'll simply save that and run that. Run it again. Now the next simulation is going to involve inviscid flow. And that is flow through a nozzle. Okay, and this requires two states, and that is in this case, a Mach state, which has a total pressure specified, in this case in PSI, pounds per square inch, 1 pound per square inch, and a total temperature, in this case in degrees Rankine. I could also use Kelvin and Fahrenheit and centigrade. In this case, the Mach number at inflow initially is 0.99, but that will go down as the simulation progresses. I'm using the van der Waals equation of state, but I could easily have used an ideal gas equation of state, and that's for the inflow and the initial conditions. And for the outflow conditions, I've created three dialogues for 0.16, 0.75, and 0.89 psi. And you can display by clicking on the boundaries, you can display the boundary condition and the reference conditions, and the outflow conditions, which in this case is 0.75 psi, and in the case of, say, this wall here is a slip condition, so there's no reference condition. This is a cylindrically symmetric simulation, and so this is a line of symmetry where y is the radial direction, and the shape here of the boundary is obtained by reading a file, which in this case was produced using Excel based on some equations, and I'm using linear interpolation in this case because I have quite a few points, but you can also use a cubic spline interpolation, and this shape is imposed on the mesh simply by selecting it from a list of options on the top wall of the grid. And again, you can use quite a few boundary conditions in the grid. In this case, we're imposing total pressure and temperature on the inflow, and a specified static pressure on the outflow, but this will be overridden by another dialog with a different state condition. It's symmetric at the bottom, and slip is indicated at the top. Close this. Now this is imposed at the exit by using a secondary boundary dialog, and all I have to do is select the appropriate pressure condition and the appropriate boundary condition, and you can disable it at selected areas. I'm using a 4-core machine, one for each simulation, and I want to preserve the 4th core for use for demonstrating how to create a script. So I arranged so that this simulation will produce a tone when it's finished. Normally it would only produce a tone or a triple tone if there's an error in the simulation when it's being run. So I'll save this script and run it and show you the final demonstration simulation before I start showing you how to create the script. This also involves inviscid flow, but in this case it will be a time accurate simulation, unsteady flow in other words, and it's a shock incident on a wedge. So there's the shock, and there's the wedge surface, and I've hidden the mesh and the boundaries so that you can see what these initial conditions are. And in this region here, you have a shock gas state. That's the post-shock conditions. And this is moving into a pre-shock condition, which is specified simply as a velocity state with, in this case, a 0.2 bar pressure and a temperature of around 300 degrees Kelvin. I'm using the argon equation state in this case. And I'm also specifying the post-front condition using this dialog here, where you specify the pre-front conditions and then specify that the shock will be moving at a speed of 2.05 times the speed of sound ahead of the shock. And I'm using a post-shock argon equation of state. And these equation of states are ideal gases. We're both using the same parameters, but different names, so I can trace the position of the post-front gas as it moves forward, as the shock moves forward. And all you have to do is specify the molecular weight of argon and the ratio of specific heats. Now, this flow region is imposed very easily. I specify the shape, which one of a few shapes, and in this case I'm simply specifying the size and the center. And if I want to input different shapes, I can do that, and they will appear on this list if I do that. And all I have to do is read in the flow region outline, which can be quite irregular, and that might be used if you're, say, simulating the diffraction of a shock front in front of obstacles and what have you. Now, EasyFlowfield can use up to 3 equations of states for different gases, and it does not simulate reactions, but for an inviscid simulation you can simulate, say, how a shock wave would have different propagation speeds in different gases. Now, this is also being run on an initial grid. In this case, it's a refined grid, and where you have 4 times the number of cells in streamwise direction, and that is basically run for a very short time in order that the shock front be more or less established before the solution is transferred to the original grid. And in this case, I'm using the 3-stage Runge-Kutta scheme. For a time-accurate scheme, you can use any of these limiters, but you'd want to use a Van L-beta limiter for a steady-state scheme if you're using an explicit solver. And you can use an implicit scheme for an unsteady simulation if shock fronts are either absent or negligible. Okay. Close that. Let's save this script. And let's just see here. It's still running, so I can wait before I start this simulation. So now I'm going to show you how to create a script. So, first you specify the type of simulation you want to create. In this case, it's steady state for 1000 cycles. This will be reduced later. And I want to produce restart files. And a restart file is something that's used to extend the simulation after it's been completed, and it also can be used to change the output variables that will be put into plot files. And this is demonstrated in another video of mine where I'm demonstrating how to create macros in ParaView, and it's the M6 wing is being used as an example. And you'd have to select this option, otherwise you select one of these options here, and that's all I have to do there. And that tone means that I can now start this simulation. And there we are. And then I come back to this, and I have to add, in this case, the states, which is a mock state. Let's see, that's the 0.8, and minus 1.25 degrees, which corresponds to an angle of attack of 1.25 degrees. And if I'm doing an implicit calculation, I don't really have to specify any of these values here. So I save this script in a pre-prepared project folder, and I'll just write over this old project script test. Okay, now I'm going to specify the shape of the airfoil, and I simply read this from this list here. Again, I could have used some other format and obtained a different format from many websites on the internet. And I wanted to specify display the curve points rather than just a black line. So there we have it. Now I'm going to use a no grid. In this case, I select the airfoil outline rather than a circle. And I'm using the standard number of cells in the chord-wise and far-field direction. This is going to be a coarse grid, and I'll make it finer later on. I'm using a chord of 1 meter and 25 meters. And if I had used my initial distance units to be feet, then I would have had 1 foot and 25 feet in this case. If I were to change the feet at this point, then I'd get something like 3+ feet for that value, and around 75 feet for this. And I'm using a standard grid layer size here, which is suitable for a chord of around 1 foot, 1 meter I should say. And I'm using a vortex correction, so I can get away with using a 25 chord to the far field. And I'm using a slip boundary condition because it's an inviscid simulation. And this is, let's see now, what else? Right, I'll close this. Now, if I were to import a grid using the GGNS and Plot3D format, then I'd have to specify a chord in this dialog, and a leading edge, trailing edge, and aerodynamic center for it. And I could specify use of a vortex correction in that case. If you're using a 3D grid for an M6 wing, what have you, this is demonstrated in another video on the M6 wing. So just delete that, not needed. And so now we're going to just have to specify what output we need. In this case we specify a number of options that are available, but all I need really to specify is pressure, speed, and Mach number. And I want to specify these values being at the cell corners, i.e. the nodes, rather than the cell centers. And I want to output it to ParaView format. That's all I need to do for that. Next one is wall values. Values along the wall. In this case, I can just specify pressure coefficient and the friction, and I want those values output to Microsoft Excel file format, but I'll be plotting it using ParaView, which is much more easy to do. And normalize X by the chord. And oh yes, if you import a grid such as a wing, a 3D grid, you can also use this input here to select the span location where you want the pressure coefficients and the friction to be output. In this case, friction will be 0 because this is an inviscid simulation. Okay, and I want to output the convergence history. In this case, I only want to output the normalized residuals, and this is an RMS average of the residuals in all the cells. I could add a bunch of other options, which I won't bother doing here. And I want it output to Microsoft Excel format. And finally, I want to output the forces along the airfoil, lift, drag, and pitching moment, again to the Microsoft Excel format. Save that, save the script, run the script in interactive mode, and that's it. Goes quite quickly. And then I'm going to plot those using ParaView. I'll get rid of this. This will be discussed in detail later. First you do is you input the file that was created. In this case, the FlowField file in this fairly coarse grid. Apply it, and then I'm going to apply a macro for mock, and the creation of this macro is detailed in another video. And simply zoom in here, and here you have the subsonic flow being accelerated to a supersonic condition on top of the airfoil, and that is terminated by an attached shock front, and it's a fairly fuzzy interface because of the coarse grid. This is shown more clearly by inputting the pressure profiles. So I'll open that. Again, wall values in this case. Apply. Select the macro. CP. And then you see I have a fairly thick shock front because of the coarse grid. The convergence is obtained by loading a state, and this state is in this case something used by ParaView to store what I've done to create these plots from input data. In this case it's going to be the convergence state. In this case here you've got something that's about less than 1/10,000th of the original value of the residuals. And finally, we want to show the force history. In this case we see we're approaching a steady state by about 1,000 cycles for the lift, the drag, and the pitching moment, which is negative. In this case the drag is being run off this scale here. Now I'll show you how to markedly improve the convergence rate. You do this by creating subgrids, doing a multi-grid simulation. And in this case, since I'm using an explicit solver, I'll also add implicit residual smoothing, which will allow slightly larger time steps. This is not much use for an implicit simulation. And I've also reduced this parameter here. And if you have very smooth flow, and then you can use, without shocks and stuff like that, you can use a larger parameter. In this case, if I use a larger parameter, then the calculations on the subgrids might prevent the residuals going down to a very, very small value. They might reach a plateau size instead. And I'm using W cycle multi-grid. In this case, I could have used other cycles as well. So I'll close that. And I'll create the subgrids. And that's very easy. In this case, no subgrid simulation will be created. This subgrid uses half the number of cells in each direction of the main grid. I'll create 2 more of these subgrids. Get a slightly different name that has 1/4 of a number of cells in each direction. And finally, subgrid 0, 0 will have 1/8 of a number of cells in each direction. Close that. Save it. Run it interactively again. And it goes quite fast because the subgrids are quite a bit smaller than the main grid, and they're just basically used to move the disturbances on the main grid out to the far field. Now the color contours and oh, made a mistake here. I'll have to reload this. This is the plot contours, and in this case I want to reload the wall values and apply that macro, and there it is again. So it's the same as it was before. Now the convergence will be better than you saw before. And there you have it here. In this case it reaches at value 10 to the minus 8 times the original value by about 700 cycles. And finally the forces. You can see here that you've reached a steady state by about 400 cycles. Now we actually want to get the solution on finer grids, and that can be done in a straightforward manner. First thing we do is reduce the number of cycles on the original grid, the coarse grid, to 400, since that's all we need. And then we add the fine grids. And we're going to run it for 400 cycles on this, what will be the intermediate grid. And this has twice the number of cells in each direction as the original grid. And I could, if I wanted, use a different CFL number for a more difficult simulation. And then one more. Fine grid 2 in this case, and I'm using 300 cycles in this case. So in this case the solution on the original grid is transferred as initial condition for the intermediate grid, and then run, and then transferred as an initial condition on the final fine grid. And just to show you how fine that final grid is, I can multiply the number of cells by 4 in each direction. This is what you get for that grid. So I don't want to actually run it using this, so I'll just delete it. Okay, and I save the script, and I'll run it in the background in this case, so I can show you something else while this is running. And that is some of the results from the turbulent flow around the airfall. So I'll read that script again. Okay, and when you're running a simulation in background mode, then it produces a listing which basically holds all the information that would otherwise be sent to the screen. The only information that's sent to the screen really is warnings and error messages. And they're also sent to this file. And even before the simulation is started, it outputs additional information. In this case, it's putting out the Reynolds number based on the reference length, which is the chord, which is 6.5 times 10 to the 6th. It also outputs the laminar boundary layer's thickness at a distance of around 1 chord, and that's really useful for laminar simulations and for some maybe simulations on a turbulent plate, turbulent flow over a flat plate, sometimes useful. Most useful is this output here, which has different values depending on whether you have a rough wall or a smooth wall. This is a smooth wall in this case, and this is the cell thickness near the wall, which would give you a y plus equal to 1. In this case, for an airfoil where it's around 1 chord in the simulation. This is a 1 millionth of a meter. And recall that that's the distance that I measured was slightly less than that previously in this video. So what you can do basically is you can run the simulation for a few seconds, stop it, look at that value, and decide whether you want to increase or decrease the input estimation of what the boundary layer size would be at the cell mid-chord region. And if you're using a wall function, then you would increase this value somewhat. And it also puts certain condition values at the end of the coarse grid simulation and also at the end of the fine grid simulation. Of most note is it gives you the maximum, minimum, and average value of Y plus in the cells next to the airfoil, and this again is based on cell thickness next to the airfoil. It also gives you the lift and drag and pitching moment, and also lets you know what the global friction, if you want, for the airfoil was, which was used as part of the calculation for drag. And if you have a rough wall, it also outputs the normalized value, roughness value, the maximum, minimum value for that. In this case, the simulation took about 11 minutes, and this is on a PC I purchased in 2014. You can probably have a much faster simulation using a more recent machine. Okay, now this simulation will have ended, so I'll then show you the results for the fine grid. First of all, remember how fuzzy this trailing edge shock was. I'll then show the fine grid result. I'll input the appropriate Flowfield value, and this is on the grid, which has 4 times the number of cells in each direction. I'll apply the macro, zoom in, and you can see that the shock is much more clearly defined. This is shown even better on the next plot. Now I input the file, And will be wall value is 5. Apply, and then there you have it. Much more closely refined, resolved shock front, and you see evidence of it attached shock as well at the lower side of the grid of the airfoil. Okay, now I'm going to show you the convergence. And there we are. Now, you're getting down to a value of about 1/10,000th again on the finest grid, and a bit better on the coarser grids. And the force is and you can see here you have the age approach steady state on the various grids, and the value of lift and drag and pitching moment is very close on the intermediate grid than on the final grid. And okay, now I'm going to start showing you the results of the other simulations that have now all ended. And first of all, I'll remove this. And the first one I'll show you involves turbulent flow around the backward facing step. And I'll just load that state. And here you're seeing velocity contours after the step, and you can also display, if you want, the region where there's recirculation of flow for the separated flow. And I can also plot the eddy viscosity. Okay. Let's see here. Right. This is a turbulent eddy viscosity. I'll just zoom out and then zoom in again. And you can see that the eddy viscosity is quite large after the step, and not quite so large in the top of this region, which is basically modeling the top and bottom of the model inserted in the wind tunnel. Next I'm going to show you the result for turbulent flow around the airfoil, RA2822. And that's this one here. This will be pressure coefficients and friction. And there you see a good match between the simulation results and the experimental results. And the same is true for the friction coefficients. And the friction here was computed in a non-standard manner. Normally, you would compute pressure coefficients and friction coefficients internally, and using the pressure on the wall minus the pressure at the far field, and divided by the dynamic pressure. The friction coefficient is just the density at the wall multiplied by the friction velocity squared, and divided again by the dynamic pressure. In this case, you can multiply by the sine of the friction coefficient. I output the friction coefficient, friction velocity and the friction, in this case here, with a negative value if there's recirculation in some region near the wall. Now, in this case, experimentally, they computed friction, but normalized by the dynamic pressure at the edge of the boundary layer. And this is very simply calculated as the pressure on the wall and the square of the isentropic Mach number. And this here is the specific heat ratio. Alright, now we'll go back and we'll show here. So you get this quite good match to experiment using the fine grid. You can get a similar match to experiment using a coarser grid with an adaptive, i.e. automatic wall function. Now I'll show you the convergence curves. And before I do that, I should get rid of this stuff. Okay, so load that state, and this is for table of convergence. So what you're seeing here is the left axis only refers to the normalized residuals. All the other stuff is referred to this axis here, which is a logarithmic axis. What you're seeing here is the ratio of the eddy viscosity divided by the maximum value of that divided by the molecular viscosity, and this reaches a constant value on the coarse grid and on the final grid, and in this case the eddy viscosity reaches a value which is a few thousand times larger than the molecular viscosity. The lift and the drag reach constant values on the coarse and fine grids, and these values are about within 2% of the experimental values of drag and lift, and if you use a wall function on a coarser grid, is actually within 0.7% of those values. And the normalized residuals reach a value which is about 1/millionth of the original value, and that's for, in this case, it's the maximum values for omega, which is one of the turbulent variables in this K omega simulation. And now I'll show you the results for EasyFlow through the nozzle. State. And this first one is for Mach number. And here you have a fairly low Mach number being accelerated till it reaches a sonic value at the throat of the nozzle, and then it reaches Mach 1.6 before it's reduced to a subsonic value because of the presence of the attached shock front. And the pressure contours. In this case, you're seeing a high pressure being reduced to quite a low pressure value, and then being increased slightly by the attached shock. Okay, now I'm going to show you the final results, which are for inviscid steady and unsteady flow. I'll load that state. And here we have it, a wedge, a shock incident on a wedge. And what you're seeing here is the pre-front pressure, the post-front pressure of the original incident shock, and then the reflected pressure. And you also see bands of equal pressure change as you move along. And I'm also going to show you the equation of state profiles, telecontours. And here you see that this is the pre-front, which has a value of 1, and the post-front, which has a value of 0 in terms of the pre-front equation of state values. And you have the contact region between the two. The post-front gas is moved with the shock but at a lower speed to this point here, and in this region here it's being pushed back by the reflected shock as illustrated here. And okay, thank you for watching. Please leave your comments and feedback and see what you think of my code.